Hello everyone, welcome back to Spectrum classes. This is our second video on the topic phase rule. In the previous video, we have discussed about the phases and how one can determine the number of phases for a given system. Here in this video, we are going to discuss what is called component for a given system and how one can determine the number of components for a given system. Since this topic seems to be very difficult for the students and they get confused while solving them or while they are determining the number of components. So here I have collected so many examples from various books and research papers also. And here in this video, I have discussed this determination of number of components by two different methods. Let's start with the term component. So what is called component? The number of component of a system at equilibrium, right? The system must be in equilibrium, is defined as the smallest number of independently variable constituents, by means of which the composition of each phase can be expressed either directly or in terms of chemical equation. So we are going to discuss the terms which we have reported here in this definition one by one. So first of all, I will explain it in two different terms. One is chemically non-reactive system. For example, if we are having sulfur, this is in solid state present in the two different crystal structure form. This is rhombic sulfur and this is monoclinic sulfur. When these two sulfur species are in equilibrium, then there is no chemical reaction takes place. So such type of systems are called chemically non-reactive systems. One more example, we are having water and here we are having ice cubes. So this is called water as liquid and this is called water as solid, right? So these two are chemically non-reactive systems, because the composition of both the phases, solid phase and liquid phase, is represented by H2O, which I have discussed in my previous video. And here in this case, the composition of both the solid phases is described by the element sulfur, right? So these two systems are called as non-reactive systems. And in my next slide, we are also going to discuss some more examples. The other term is chemically reactive systems. When we are having such type of systems which are in equilibrium, they reacted with each other. For example, if I am having a glass of water and to that glass of water I am adding spoon of table salt, then what is going to be happen? Here this is water and this is sodium chloride. When these two are mixed together, then it undissociated or the solid NaCl is converted to Na plus Cl minus. And one more thing, when I dissolve this 1 spoon of water, then how many phases are there? Since we are having soluble NaCl in water, so one phase will be there. Now we are coming to the chemical species. So first we are going to discuss about the chemically non-reactive systems. So here we are having the example of water. Water is present as ice, as liquid water and as vapors. So if these three are in equilibrium, here for water we are having three phases. One is ice, solid, liquid and vapors. And how we are going to express their composition? So all three, whether it is in solid form, liquid form or in vapor form, it will be expressed as by the formula H2O or water. So number of components for this system, which is having three different phases, is equal to 1. So only one species is required to express the composition of all three phases. Now coming to the next example. Can you guess what is this? Yes, you are right. This is dry ice. What is called dry ice? So dry ice is CO2. So this is exist in three different phases: CO2 solid, CO2 liquid, and CO2 gas or vapor. So number of phases are three again, just like water, and composition of all three phases can be represented by chemical formula CO2. So this system is again one component system. Now coming to the sulfur. So here we have already discussed. So this sulfur present in two different solid forms. One is rhombic solid and the other one is monoclinic solid. This is also present as sulfur liquid and as sulfur vapors. So how many phases are there? So here we are having four different phases because these two are considered as different phases because these two are mechanically separable. So number of phases are four, and how we are going to express the chemical composition of all four phases? So that will be expressed by the element sulfur. So this is again a one component system. Now coming to the mixture of gases. If we are having non-reactive mixture of gases A, B and C, suppose A is hydrogen, B is helium, C is argon. This is again a non-reactive system. That is, these gases are not reacting with each other. Phase, since these are all are in gaseous phase and mixture of gases constitutes one phase only. And now coming to the number of components. So to express the chemical composition of this system when it is present in equilibrium, we have to specify hydrogen, helium and argon. All three we need to specify to explain the composition of this system. So this is a three component system. So here we have a generalized formula. If non-reacting mixture of gases we are having, then the number of components will be equal to the number of gases. So it is three component system. We are coming to the chemically reactive systems. So before discuss the examples of chemically reactive system, we are having certain rules for this type of systems. So here I am just summarizing those rules. So in chemically reactive system, the number of components will be given by this formula. So C is equal to capital N minus small m minus small n minus capital R. What all these terms signifies? So capital N is equal to the number of chemical species. Small m is the number of independent equilibrium conditions. Small n is the number of relations between concentration due to initial conditions. And capital R is the number of independent chemical relations. This formula can further simplified in terms of component is equal to number of chemical species minus number of chemical reactions, which is represented by this capital E. E stands for equations. So here what is E? Number of independent equations relating the concentration of n species. So here n is the species and E is the number of equations relating their concentration. In some texts it is also mentioned as number of restrictions imposed on the independent variation of these constituents. Guys, if all these terms seems to be heavy for you, so please wait. In the next slide, I will explain each and everything with example. That will make this slide little easier for you to understand. Now, how we are going to discuss this? So I have collected two more points. These 2 points we are going to discuss in the next slide. This chemical formula will also be expressed as C is equal to number of species minus number of equations relating to their concentration minus 1, and this 1 stands for the electrical neutrality, which is considered as one equation. All these terms, whatever I have written here, I will explain one by one with the help of examples. So first we will start with the example of aqueous solution of NaCl. So as we discussed in our previous slide, here we are having a system. In 1 glass of water, I am adding some salt. And here, this is water. The chemical composition of water is H2O and this salt is NaCl. Once this salt is dissolved, we will get this type of picture. So how many phases are there? There are only one phase, right? Now the question is how we are going to express number of components for this given system. So here, since H2O is there and this NaCl, solid NaCl is not there here in this glass, we are having only Na plus Cl minus. On dissolution, it dissociates into its ions. Here, number of chemical species, which is represented by this capital N. So how many chemical species are there? 1, 2, and 3. So we are having 3 chemical species altogether while we are dissolving this NaCl into water. Now coming to this formula which we have discussed in our previous slide, that number of components is equal to number of species minus number of equations relating to their concentration. And here each equilibrium, the number of equilibriums which are existing in these number of species, or if we are going to express these number of species for a given system in terms of equilibrium equations, then each equilibrium will be considered as one equation. So E will be 1 for each equilibrium. And second point is that if we are having ions present in the system, then we will consider the electrical neutrality. And that is also considered as one of the equations, right? Since we are having the ions in this system, so electrical neutrality must be there, that is Na plus will be equal to Cl minus. So this is one relation or one restriction which is imposed to this system, and therefore this will be considered as one equation. In some texts, this formula is also represented as N minus number of equations relating to their concentration minus electrical neutrality. And since electrical neutrality is represented by 1, so this formula can also be written like this, or we can add this 1 to the number of equilibrium equations that we are going to discuss in the next slide. So here, if we are considering this formula, so no equilibrium is there. Therefore, this E is equal to 0 and N minus 1. So N is 3 minus 1. So either you can consider this or you can consider this only by adding the electrical neutrality to the number of equilibrium equations. So here what we get, number of components is equal to 2. What does it mean? It means how we are going to express this system in terms of number of components, the smallest number of species which are required to express the composition of this system. So we require 1 water, and since here this Na plus is equal to Cl minus, so if we come to know Na plus, then due to this restriction that Na plus is equal to Cl minus, so Cl minus can be evaluated, right? So H2O is required and Na plus or Cl minus. Out of these two, if we come to know 1, then by that concentration of Na plus or Cl minus, we can fix the other one. So this is how minimum 2 chemical species or components are required to define the composition of this system. So this is one example. Now coming to the next example. Here we are having supersaturated solution of NaCl. So in the previous example, what we have discussed, to this point we have discussed, and this is a 2-component system. Now coming to the supersaturated solution. So what supersaturated solution is? If we are keep on adding NaCl to this till the moment when there is some undissolved NaCl is there, means no more NaCl can be dissolved to this quantity of water. So this is a supersaturated solution of NaCl. So what inference from this picture you can make? Number of phases for the system is 2. One is solid phase and one is liquid phase, right? So this is how number of phases can be represented. Now coming to the composition part. So here we are having 3 species. H2O plus Na plus Cl minus, and here this solid phase can be represented by NaCl, means undissociated NaCl. So I'll explain this system in the next slide in detail. So here what we are having, these are the number of species. Now number of species for this system is 4. In the previous case that are 3, because undissociated or solid NaCl is not there. Here we are having solid NaCl2. So number of species 1, 2, 3 and 4. So 4. Now the next step, what we have to do after this determining number of chemical species, we have to establish the number of equations which are present in this given system. So first, since Na plus and Cl minus ions are involved, so electrical neutrality will be considered as one equation. The second thing is that NaCl is a salt and it dissociates completely. As we all know, salts dissociates completely and it is not represented by the equilibrium condition, right? But here this NaCl and Na plus and Cl minus are present in the equilibrium. How we are going to justify this? Because NaCl undissociated and dissociated is present in this system, therefore we established one equilibrium condition. Some of the students are also confused with this equilibrium sign which is placed here with NaCl. Why it is so? So this is maybe answer your query. So since if solid is not there, then no equilibrium will be there. Because of the presence of solid, there is equilibrium. So this equilibrium is considered as one equation, and since ions are present and to that ions a restriction is imposed or their concentration condition is there, therefore electrical neutrality will also be considered as one equation. So here we are having equation 1 and here we are having equation 2. So this many equations are present for this given system. Now coming to the formula for calculating this number of components. So number of components is equal to number of chemical species. So that is 4 minus number of equations relating to their concentration, here 2. So 4 minus 2 will gives us 2. So there we require 2 components or 2 smallest number of components, chemical species, to define this system. How we are going to explain this? So for this system we require Na plus or Cl minus concentration, and that Na plus and Cl minus concentrations are related to this NaCl. So one water is required, right? So this is how one can determine the number of components for a given system and what components are required to define the system. Now coming to the question part. Suppose we are having a question in which decomposition of NH4Cl solid is given, and the conditions are reaction is carried out in a closed vessel. It can be given like this, or this condition can also be written like this: the partial pressure of NH3 gas is equal to the partial pressure of HCl gas. Or these two statements can simply be written like this, that P stands for pressure of NH3 will be equal to pressure of HCl. Right, so in these, out of these three forms, this decomposition of NH4Cl can be given. So how we are going to solve this? So first we will write the decomposition of NH4Cl solid in terms of equilibrium condition. So here we are having NH4Cl which is in equilibrium with NH3 gas plus HCl gas, and this can be represented in this vessel. This is just a representation. Suppose this is the solid NH4Cl and this dissociates as NH3 and HCl, and the condition is given that partial pressure of NH3 is equal to the pressure of HCl, right? So here we are having two equations. One is this, second is this, and no ions are involved in this system, right? So we are having number of species 1, NH4Cl solid, NH3 gas, HCl gas. So number of chemical species are 3. Number of phases we are having 2. One is solid and the other one is gaseous phase. So here we are applying this formula to count the number of components. C is equal to N minus E. So N is what? N is 3 and E is 2. So C is equal to 3 minus 2. This is one component system. And what is required to determine this system or to explain this system? We need NH4Cl to explain the composition of this whole system. This is the method by applying this equation C is equal to N minus E, and now I will explain you in a detailed manner. So if equilibrium exists, so here this pressure equilibrium constant is given in terms of pressure of NH3 into pressure of HCl divided by pressure of NH4Cl. Since NH4Cl is solid, therefore its pressure is counted as 1. This equation will be written like this. So by the knowledge of equilibrium constant, one can apply that condition here, since it is given that partial pressure of NH3 is equal to partial pressure of HCl. By putting that value, one can evaluate the other one. Right? So that is why this is one component system. And since it dissociates into NH3 and HCl, so if we combine these two, we will again get the NH4Cl. So out of these three, we need to know this NH4Cl, which represents the solid also. So solid dissociates to NH3 plus HCl. The rest thing one can determine from these equations, right? So this is how we can say this is one component system. So the composition of solid phase is given by NH4Cl and the composition of gaseous phase will be given by this NH3. This NH3, if we come to know this NH3, we can determine the HCl, and if we combine them, we will get NH4Cl. So only one component system or only one species is required to define the whole system. Suppose this same question is given in this manner. Decomposition of NH4Cl solid carried out in open vessel, or partial pressure of NH3 gas is not necessarily equal to the partial pressure of HCl gas, or PNH3 is not equal to PHCl. So first, how we are going to solve this? First, again we write the same equilibrium equation, and now I'll just represent this in the open vessel. Here we are having NH4Cl and this is NH3 and HCl. Open vessel means the HCl and NH3 are not same, because if environment contains the NH3 or HCl, then their concentration or their partial pressures will not be the same. Now number of species. So 3 species are there again, NH3, HCl and NH4. This can also be evaluated from the equation. Now coming to this equation, C is equal to N minus E. So number of species are 3 and number of equations or restrictions imposed to the system is equal to 1. No ions are involved and no other equation is existing in their concentration terms. So the number of components for this open vessel system is equal to 2. So it is a 2-component system. So one, to define this solid phase, we require NH4Cl, and out of these two gases, at least one gas must be known to us for this equilibrium constant. In terms of equilibrium constant, this can be calculated like this. Since NH4Cl is equal to 1, so here we are having this PNH3 into PHCl. Since from the equilibrium constant condition we can evaluate only one term from one equation, and since PNH3 is not equal to PHCl, so one species must be known to us for this equation, right? So composition of solid phase will be given by NH4Cl and composition of gaseous phase is given by either in terms of NH3 gas or in terms of HCl gas. What has happened to the previous case? These two are same. So on adding these two, we will get again NH4. So both the phases will be represented by NH4Cl as compound. But here, since these two are not equal, so we are not getting NH4Cl as a whole, right? So it is a two component system. So to define the solid state, we need NH4Cl, and to define the gaseous phase, we require either NH3 or HCl.